Today's numerical is a cast iron beam 2.75 meter long has one support at left end A and other support at B. One support A is hinge support and B is roller support. B is at 0.75 meter from end C. The beam is of T section consisting of a top flange 150 mm by 200 mm, 20 mm, 150 mm width and 20 mm depth for this second flange, top flange, and wave of 20 mm wide and 80 mm deep. If the tensile and compressive stresses are not to exceed 40 Newton per mm square and 70 Newton per mm square respectively, find the shape concentrated load W what can be applied at the right end of the beam. So we have to calculate shape concentrated load W, this W. And in numerical, they have given us maximum tensile stress is 40 Newton per mm square and compressive stress is 70 Newton per mm square. That means sigma max for for tensile is not to exceed 40 MPa and sigma max for compressive not exceed 70 MPa. See cross section of this beam, top flange 150 mm wide and 20 mm thick, and this web part is 20 mm wide and 80 mm thick. So for the given beam, only hogging moment produces the section. That means this given beam moment is only hogging moment. See, deflected shape of this beam is like this. And due to this W load, only hogging moment produces, and this hogging moment is denoted as M, and E is equal to W into 0.75. That means 0.75 W. This W and 0.75. This is hogging moment. Now next calculate position of neutral axis for this T section. Y bar is equal to this wave part is 1 and top flange part is 2. A1 Y1 plus A2 Y2 upon A1 plus A2. A1 is this bottom wave area 20 mm multiplied by 80 mm. One six zero zero mm square. Y1 is distance from this bottom fiber, to mid of this wave part. This wave is 80 mm, that means 80 divided by 2, 40 mm here, 40 mm. Now A2 is top flange area. Top flange dimensions are 150 mm cross 20 mm. That means 3000 mm square is area of this top flange. And y2 is mid distance of this top flange from bottom fiber. From this bottom fiber to mid of this distance is, see, this wave total depth is 80 mm and plus this 20 by 2 is 80, and this much distance is 20 by 2. That means 80 plus 20 by 2. $90 mm. Now calculate y bar is equal to 1600 multiplied by 40 plus 3000 multiplied by 90 divided by 1600 plus 3000 is 72.61 mm. Each position of neutral axis. This 72.61 mm is position of neutral axis from bottom for this T section. Now next calculate moment of inertia for this T section. Moment of inertia I is equal to, this bottom wave part is Ixx1 and plus top flange part is Ixx2. So first calculate, see, position of neutral axis is this here, and from bottom this position of neutral axis is at 72.61 mm. And only consideration of this wave part, see, only this wave part consideration, only this wave part neutral axis is 40 mm. 80 divided by 2, 40 mm. So that means someone here 40 mm. And total T section neutral axis is this sky blue color. And this red line is x1 and this sky blue line is x axis. Total T section axis neutral axis x axis. So first we have to calculate this red line x1 axis moment of inertia for this wave part. So this is parallel to this x1 axis is 20 mm dimension. So 20 mm as it is, multiply by this 80 cube, 20 multiplied by 80 cube divided by 12, right? Plus area of that wave part is 1600 and multiply by distance between this total T section neutral axis and only this wave section neutral axis. That means distance between x axis and x1 axis. This distance is 72.61 minus 40 mm. It's 32.61. This yellow color line distance is 32.61. And square of this. With the help of parallel axis theorem, we calculate moment of inertia for this T section. Next, calculate this x2 axis. Wave part mid axis is x2 and this x2 is from bottom tensile fiber distance. This x2 distance is this y2 distance 90 mm. This 80 mm plus 20 by 2 90 mm. So calculate moment of inertia for this x2 axis is 150 mm parallel to this x2 axis. So 150 add is multiply by this 20 cube divided by 12 plus area of this flange part is 3000 mm square and multiply by distance between this distance between original T section neutral axis to only this top plane neutral axis, distance between this and square of this distance between this is 90 mm minus 72.61, so 17.39. So right here this x2 axis parallel distance is 150 as it is, multiply by opposite side distance is 20 and cube of this opposite side distance divided by 12 plus area of this top flange part 150 multiplied by 20 3000 multiply by distance between T section neutral axis and only top flange neutral axis is 17.39 mm. Square of this distance now calculate 1600 multiplied by 32.61 square plus 20 into 80 cube divided by 12 is 25.55 into 10 raised to 6 for this only first part, 25.54 into 10 raised to 6 plus this 3000 multiplied by 17.39 square plus 150 into 20 cube divided by 12. One into 10 raised to 6. So calculate this value again. 1600 multiplied by 32.61 square plus 20 into 80 cube divided by 12 is 2.54. Here 25 not 2.54. into 10 raised to 6 plus 1 into 10 raised to 6. 2.55 plus 1 is 3.55 into 10 raised to 6 mm raised to 4 is moment of inertia for that T section. This is moment of inertia for that T section about x axis. 3.55 into 10 raised to 6. This is neutral axis. Top side sigma c, sigma t. This distance is y bar distance 72.61 mm. And top side distance is this 80 plus 20 100 minus 72.61. That means 27.39 mm. This is YC and this is YT. With the help of this stress distribution diagram, see YC upon YT, similar triangle theorem is YC upon this YT, sorry, sigma C upon sigma T is equal to YC upon YT. And in numerical, they have given us sigma C or sigma T. Sigma T is 40 MPa or sigma C is 70 MPa. So let sigma C is 70 MPa. Why we calculate or take this step? Because check for this sigma T. Check this sigma T value is less than this 40 MPa. So sigma, put sigma C is equal to 70 MPa and put YC is equal to this 27.39 MPa and YT is this 72.61 mm. YC is mm in mm. So sigma T is equal to YC upon YT multiply by sigma C. YC is 27.39 mm divided by YT is 72.61 mm multiply by 70 MPa. Now check this sigma T value is greater than 40 MPa or less than 40 MPa. If it is less than 40 MPa, then it is safe. So 27.39 multiplied by 70 divided by 72.61 is 26.41 MPa. 26.41 MPa. Stress at tensile side is less than 40 MPa. That means okay. Because in numerical, not tensile stress not to exceed 40 Newton per mm square or 40 MPa. So this is okay. Now next, calculate moment of resistance. For calculation of moment of resistance, use bending formula. Using bending formula, m by I is equal to sigma by y is equal to E by R. we have sigma, we have y, and we have I. So use these first two equations. Therefore, m is equal to sigma by y multiplied by I. This YC, use maximum Y. YC 72.61 mm and sigma T is 26.41. See, this YC is 72.61. No. Yet something is YT. So see here, we take one mistake. See, if this beam deflect like this, see, if this beam deflect like this, hogging moment generates, and hogging moment, tensile forces acts on top side and compressive forces act on bottom side. So here, this top stress is tensile stress, sigma T. Sorry for that, our numerical is correct, our solving methodology is also correct, but in last step, correct this sigma T and sigma C. Here also YT and YC. This is also correct because in similar triangle, bottom sigma C upon sigma T or YC upon YT is correct. Okay. Only for this part, here use maximum Y, because if Y maximum, then this sigma is also maximum. This Y is directly proportional to sigma, so use Y maximum here in this equation. That means use YC. And if we use YC, that means use sigma C also into I. Therefore, m is equal to sigma C is 26, sorry, sigma C is 70 MPa. Yes, sigma C is 70 MPa. Use maximum sigma C for that moment of resistance. YC is 72.61 mm and multiply by I, moment is this 3.55 into 10 raised to 6. Now this is moment of resistance for this T section is 70 into 3.55 multiplied by 10 raised to 6 divided by 70.72.61 is 3.42 into 10 raised to 6. And this sigma is in MPa, this YC is in mm. See, MPa, that means Newton per mm square. This I is in mm raised to 4. This YC is in mm. So mm square and here mm square. This mm cancel. That means this moment of resistance is in Newton meter. And convert this Newton meter value, Newton mm value into kilonewton meter. That means 3.42 kilonewton meter. This 10 raised to 3 get cancelled for Newton to kilonewton, and 10 raised to 3 again get cancelled for mm to meter. So 3.42 kilonewton meter is moment of resistance. Our objective of this question is calculate safe concentrated load W, this load. This W load calculate. For calculation of this W load, equate moment of resistance with moment of this beam. Now equate moment of resistance with moment of this beam. So moment of resistance with moment of resistance is this 3.42 kilonewton meter, and moment is this 0.75 W. So W is equal to safe load or safe concentrated load W is 3.42 divided by 0.75. That means 4.56, and unit of this is C, 4.56, and this MR unit is kilonewton meter, and this moment unit is also in kilonewton. See, W is in kilonewton meter. W is in kilonewton, sorry, W is in kilonewton, and this 0.75 is in meter. Sorry, something is on here, kilonewton meter, and here. So this W is in kilonewton. Because concentrated load W is in kilonewton. So see here, this T section dimensions are 150 mm cross 20 mm flange, top flange, and wave is 20 mm thick and 80 mm deep, and this beam is this. See, A is hinge, B is roller, and between B to C it is cantilever part with concentrated load W act on point C, and for that moment is hogging moment 0.75 W. Position of neutral axis is 72.61 mm, for that total depth 100 mm. Moment of inertia is 3.55 into 10 raised to 6 mm raised to 4. Tensile stress comes 26.41 MPa, and it is less than extreme or maximum tensile stress. That means this is okay. And moment of resistance is 3.42 kilonewton meter. For equilibrium, equate moment of resistance with moment, we get W, and W is concentrated load at point C. Here is 4.56 kilonewton. Thank you very much.